Okay, now I got the sign to start from all the technicians in here. Welcome all of you who are out in the cyberspace. You're most welcome to this dissertation and public defense in computer and system science. My name is Mårten Sjöström and I have the honor to chair this session. Firstly, I'd like to present the respondent, who is the main figure and the reason for us to be here today. His name is Waqas Ahmad. He will come up here later and you will see him. He got a Master of Science in Electronic Engineering from the Muhammad Ali Jinnah University in Islamabad from 2012. He's also been working in industry as a senior design engineer, senior software engineer and lecturer, and was then accepted as an early stage researcher in the Marie Sklodowska-Curie European Training Network on full parallax imaging. And during this employment that was here at the Mid-Sweden University, he has been pursuing a PhD. During his time here, he has also initiated new collaborations and obtained a grant from the Swedish Foundation for International Cooperation and established a research collaboration with Comsat University in Pakistan. So we are grateful for that, and we're grateful that you are here today. Secondly, I'd like to welcome our second main figure today, which is the opponent, which is Professor Peter Schelkens. He's sitting in Belgium. He got a PhD from Vrije Universiteit in Brussels in 2001 and has been a professor at the same university since 2005. He has also been a principal investigator at EMEC in Leuven, Belgium since 2020. And if you look through his CV, he has plenty of awards, and he's also involved in JPEG plano standardization work. So he's a very good person to have here today, as the work that Waqas has been doing is highly related to that. With us today, we also have the examination board, and the following distinguished members are Associate Professor Markus Flierl from KTH in Stockholm. He's got a PhD in electrical engineering from Friedrich Alexander University in Erlangen-Nürnberg in 2003, and since 2009 he's an associate professor at KTH in Stockholm. And he has also very nice awards on his CV. Next person is Thomas Wiegand. He's at Technical University Berlin and at Fraunhofer Heinrich Institute. He got his PhD in 2000 from University of Erlangen-Nürnberg, the same as Markus. He's a professor at the Technical University and also the head of the Fraunhofer Heinrich Institute in Berlin. He has actively, Thomas Wiegand has actively participated in the standardization of multimedia and he has been a co-chair for the ISO IEC MPEG video and also a chair of the ITU WHO focus group on artificial intelligence since 2018. The last member of the examination board is Professor Jonas Unger from Linköping University. He's got a PhD from 2009 in visualization media technology and became a professor in 2018 at the same university. From the same year, he's also a cluster leader in interaction and communication with sensor-rich autonomous agents at the Wallenberg Autonomous System and Software Program, a very large program in artificial intelligence here in Sweden. He's leading the visualization research within MedTech for health, advanced imaging and data analysis at Linköping University, and he also has a lot of nice awards. Additional persons here today, not in the room, but in cyberspace. I am here in the room. I'm the main supervisor of Waqas. So I'm a professor in signal processing here at Mid-Sweden University, and I'm heading the group of Realistic 3D. Co-supervisor is Dr. Roger Olsson. He got a PhD here from Mid-Sweden University in 2010, and has also been a senior researcher here at the university since then. He was actually one of the earlier adopters of light field compression back in 2006, so he is a very good person to have as a secondary supervisor. So this dissertation starts with that the opponent will give a brief introduction to the field of the dissertation. Then the respondent will give a summary of the thesis. We probably need a short break after that, after listening, because that will take about half an hour, 40 minutes, something like that. And thereafter, the respondent, Waqas, and the opponent will have a discussion for some time, as long as it takes, and usually that is an interesting part for both us here in the room and for the respondent and the opponent. Thereafter, the examination board will pose questions to the respondent. Still, the public is not allowed to intervene, but you will have your chance after that and pose questions to Waqas about his work. When that has been finished, we will have a short break again, and the examination board will recess to decide the verdict, pass or not pass. Now, the next thing I'm going to do is ask you, Waqas, whether there are any errors of forms in the thesis or in your work.
There is a typo in my thesis on page number 27 in equation 5.1. I missed to report a rounding operation.
Okay.
And there are few typos in my published paper, but since my correct codes are already available, so that's not affecting anything. Yeah.
Okay. So then I hand over the word to the opponent, Professor Peter Schelkens.
Yes, thank you very much. So let me try and see whether I can share my presentation with you, which is often also a challenge in virtual space. Well, in physical space, we're often struggling with the projector, and now I'm struggling with my interface here. Just a small second. Okay. So I don't know whether you're seeing the presentation of my presenter's view.
We actually see your presenter's view.
Okay, so let me try to see whether I can switch this.
So if you just click the
displays
to the left. Yeah.
Is this fine?
Yeah, this is fine. We see your presentation.
Okay, excellent. And you see yourself as well, I believe. It is done. Okay, good. So first of all, I would like to thank University for inviting me to act as an opponent for the PhD defense of Waqas Ahmad, which has as topic high efficiency light field image compression. And so to introduce this work, I would like to first actually situate a little bit the domain in which this work is actually being positioned. And so you can actually position the work in the broader domain of immersive media, which is really, let's say, the hot topic in media research these days, trying to come up with, at one side, visualization technologies that allow you to really get embedded into a virtual scene, so much better than we are actually experienced today in this Zoom meeting. Where different type of technologies, display technologies are currently being devised, ranging from head-mounted displays up to high resolution, multi-view type of displays. And I will focus a little bit more on that in the coming slides. And of course, there is also the challenge in parallel to capture and generate this information. And there is a plethora of imaging techniques that is popping up. And of course, also on the computer generated side, interesting evolutions are taking place. And actually, where I would like to focus a little bit more on this in this introduction is actually the representations that are typically being used to represent this media content, because typically what you want to represent here is actually the 3D scene that you're looking at. And so that means that it is different types of information that you need to capture. You need to capture actually the location from where particular visual information is coming. You need to capture the color. You need to capture the time aspects of it, and so forth. And so this is actually, you can describe that by one mathematical function, which is basically called the planoptic function, that describes actually all the visual information about the scene or the part of the scene that you are actually observing. And you can imagine this a bit more intuitively by assuming that you have a small pinhole camera, and that with the pinhole camera you're taking actually images from all possible positions, possible angles and positions in the space, such that you can get actually a very complete representation of that 3D space. Okay, and if you have a video camera, you get also the time dimension there at the same time. So this kind of an intuitive way to understand actually what that planoptic function is describing. Now, there are, of course, different ways, because the pinhole camera is actually, let's say, a more theoretical view to look at it. There are many ways of how to collect that information, and to make it a little bit more concrete. There are a number of modalities in which you can capture that information. Say the most easiest one is the one that you see here. Is we have taken a very simple scene of a head of a statue. Is to take a camera and take pictures from different positions. So that's what you can see here. So you can assume that camera to be the pinhole camera that is moving around on the scene and takes from different angles and position a picture. And so this is the result, and that's actually what we call a light field. So a representation of a light field, which is actually exactly the topic of the PhD dissertation, which is defended today. But besides that, there are quite a few other types of ways to represent this data. So we call these all kind of planoptic representations. So a very simple one is here, you can see on the left side here, is you take one picture that contains basically the texture information of the scene, and also the color. It's here in black and white, so grayscale, but in principle you can take it in other. You can collect the color information as well. And a second image that contains the depth information of the scene. So for every pixel here, you have a pixel here that indicates, okay, how far away basically that pixel is from the camera. And that gives you, both information gives you some idea about the 3D composition of the scene. Another way to do that is to use, for example, a point cloud. So what you see in this image is just a collection of dots, of points, which are positioned in a 3D space. And altogether, they also allow you to describe basically the shape of an object, and you can add color information to it, and so forth. So this is a very popular representation these days as well. And then another one that situates also in this planoptic domain is what we call holographic representation. So that's a little bit the a strange or a deviating type of representation, because while the other ones here are all assuming that light is propagating as rays through space. Okay, it's an approximation, but propagating as rays, which makes it very easy to manipulate it, to do calculations on it. In the holographic case, we don't look at light anymore as rays, which are going through space, but as waves. And so three-dimensional waves, which are just propagating in space. You can compare it basically when with a situation where you throw a stone in a pond, and that you then see like the oscillation spreading out of the pond. Well, actually, this is a principle that is also being used in holography, by which we can then describe 3D scenes. So what you're measuring here and recording in the hologram are just is actually the superposition of all the waves that are coming from the 3D scene. And in order to do this appropriately, you have to store amplitude information, and you still need to store also phase information. And these two informations together allow you to reconstruct the full wavefront of the 3D scene. So it's a bit more complicated. And so if you want to go to then to 3D visualization, and so I've took here a slide which comes from a publication of Smalley, which actually provides a very interesting overview of the three main ways to represent this planoptic information, then you get this situation here where, okay, I will talk about the light field at the end, because that's where we're finally going to end up in the discussions today. So if you would start from, for example, this point-based representation, so what you typically will create are displays, which are basically behaving like typically kind of a cube that you will have in front of you, where you're able to actually enlight various positions inside this cube. And by enlighting those positions, you will see actually a 3D rendering of the scene. So the advantage of this method is that it's relatively easy to create the perception of parallax and so forth. So it's also relatively easy to control. You have no accommodation problems. That means, okay, for example, with some kind of representations, for example, when you use head-mounted displays, it can be very hard to actually support your eyes in a decent way without creating any conflict between focusing of your eyes and then actually the orientation of your eyeballs. So this is called the divergence accommodation conflict. So it's not a problem at all over here. The problem you have with this kind of displays is that you have a very hard time handling occlusion effects. So when a certain object is behind another object, okay, so since you're eliminating all the necessary points, you have a kind of transparent type of display, and you see all the layers of the scene, and that might create some disturbing artifacts. So these are more or less the most important aspects. On the holographic case, actually, there also parallax can be supported very easily because it's contained in the amplitude and phase information. So there is absolutely no issue also with respect to accommodation. Occlusions are automatically handled as well, though it requires some processing if you're computer generating those holograms. Supporting wide viewing angles. Okay, is here a problem? While with the point cloud display, you can just walk around this display and you can see from every angle basically the point cloud and the 3D scene. For those holographic displays, you need extremely small pixels in order to have them behaving like diffractive units. And so that means you have to have pixels which are in the order of, you have a pitch size which corresponds to the wavelength of the light that you're using. Okay, actually half the wavelength. So that means that you need very tiny pixels. And the bad news is that we're not capable of producing those currently. Many people are chasing this holy grail, but we're not there yet. And then where we will be talking about today is the type of light field display. And so also here, when you look at this most prominent properties, then also there it's easy to support the parallax, and I will need to show you an example on the next slide of such a display. Accommodation is a bit harder because the problem here is that you have to determine upfront a particular focused instance, and then you're providing a whole set of views for that particular focal distance when you're displaying it. And that might create annoying divergence accommodations conflicts if you don't do it hard. It's solvable, but it requires some effort. While in the other two cases, this is almost automatically being offered. And another issue is also here that supporting large viewing angles is possible. So there are displays that support 180-degree viewing angles, so you can really move around the display and see a scene in 3D from different positions. But there are also physical limitations to it, because in order to really get then sufficient number of viewing angles to have like smooth transition between all the different views, the problem is that you need small pixels. And when you reach the size that is needed for that, they start behaving as diffractive units, and then you end up in the holographic case. So there is a smooth transition between those two types of displays. But it's a very promising, and I think it's at this moment the area which most people are chasing, and to have really very nice 3D displays. And so that means, of course, if you want to create content for this type of light field displays, that you need the necessary capturing equipment. So the good news is there are some planoptic cameras around that allowing you to capture actually a light field. So you see an example from a company called Raytrix here on the scene, and the principle that is being used, that besides the regular lenses you have in a camera, you have also a small array of micro lenses into in this camera, and they will actually locally record information coming from different viewing angles, and in that way you will basically be collecting your light field. And on the display side, you can use similar principle, also using those micro lenses on top of the pixels, and you will take care that every pixel produces lights that then goes out in a particular direction. And in that way, you can actually support multiple views depending on the position you are in front of the scene. There are other technological ways to realize this, and I don't want to focus on this here, and I'm sure that Waqas will give you more details on this. But the big problem, and that's actually the topic of this thesis here, is that, of course, you have to get the data from the camera on your display. And typically, if you think about like broadcasting applications and so forth, you will have to transport this information over a network. And so the big problem is that this network might well be the bottleneck to transport your data. Why? Well, because instead of having one image per time instance that you are consuming, like in a video sequence, you have n images, and this number can be quite high, and that means also that you get n times. Okay, then you need n times the bandwidth that you need for a regular image, and this can be quite high. And so this really puts a lot of stress on nowadays computer networks if you want to massively actually roll out this type of technology. And so this is exactly the focus of the thesis, having efficient algorithms to represent and compress actually a light field such that you can easily transport it over the network. And so this concludes also my overview, and I hope this is a good introduction for the work that will be presented now by Waqas. Thank you.
Thank you very much
for this introduction to the field. Now I will give the floor to the respondent, Waqas Ahmad.
Thank you, Professor Peter Shankar, for your nice talk on immersive multimedia and to introducing the domain in which my thesis lies. I would like to welcome the examination board and the participants who are watching me on Zoom and who are watching me on YouTube. My name is Waqas Ahmad, and today I will present my research work on light field image compression. The topic of my PhD thesis is high efficiency light field image compression, hierarchical bit allocation, and Shearlet-based view interpolation. These will be the contents of my today's presentation. Initially, I will introduce the research area in which I was working, and then I will explain the research problem which I have solved in my thesis. Then I will explain the verification methodology that I followed to solve the problem. Later on, I will explain the overall aim of my work, which is further divided into two purposes, and both purposes resulted into a compression solution. So I will cover each compression solution in detail. And finally, I will conclude my talk and I will give some possible future direction out of this work. My PhD research work concerns with visual information and compression, and both of them are playing an important role in our society. For example, before COVID-19, these PhD defenses were organized in person. So the grading committee, the participants, the PhD student, they all appear physically. However, in these times, we are making use of communication technology to fulfill this requirement. And in this process, visual information and compression, they are playing an important role. Similarly, the influence of visual information in our daily life is increasing in the form of multimedia applications. And in these applications, again, compression is a critical aspect. To provide an immersive presentation of visual information, light field imaging technologies were introduced to capture the spatial and angular information of the scene. The captured data is mainly represented by following two-plane parameterization of light field as shown in the figure, where the intersection of light ray is parameterized by its intersection with two parallel planes. One plane represents the camera plane and second plane represents the image plane. Light field imaging enables various post-processing applications such as refocusing, 3D scene reconstruction, and many more like that. And its footprints can be seen in some other fields as well, such as microscopy, biology, robotics. In comparison with conventional images, with whom everyone is familiar with, the conventional image captures the spatial information of the scene. So, it is a single view of the scene. On the other hand, in light field images, it captures spatial and angular information of the scene. It is a multi-view of the scene. In general, light field is usually captured using either single panoptic camera or using multi-camera system. In the case of panoptic camera, the spatial and angular information is captured onto a single image sensor with the help of microlens array. In the right figure, the optical setting of panoptic camera is shown, which is used in my research thesis, where a microlens array is placed in between main lens and image sensor in such a way that each microlens captures the angular information of the object points that are focused by the main lens. On the left side, the resulting panoptic image from panoptic camera is shown, and a zoom version of this image shows the microlens images captured behind each microlens. In the case of multi-camera system, traditional cameras are mounted onto a planar surface, and each camera captures a specific perspective of the scene. Light field imaging also brings several research challenges, right from its capturing till its presentation. In particular, researchers are focusing on lens aberration, especially with the introduction of microlens array in this optical settings. Then they are also looking into calibration, since multi-camera systems are employed to capture the light field, and also working on reconstructing a full light field image using demosaicing techniques, and also compression, in which I worked, and then different other fields like disparity estimation, view synthesis, quality assessment, and displaying the light field information. So, the problem here is quite straightforward. In the pursuit of capturing the spatial and angular information of the scene, light field devices capture large amount of data, which contains high correlation as well. So, efficient compression solutions are required to compress this information. Here, few examples of light field that is captured using panoptic camera and multi-camera system are shown. In the research of lossy data compression, the data, which can be image, video, audio, is compressed with an appropriate compression scheme on different bit rates. And on each bit rate, the quality of reconstructed signal and the original signal is measured. This rate and distortion measure is used to benchmark different compression methods. This is one of the main criteria to evaluate different compression methods. With the growing interest in light field compression, recently the coding standardization body, Joint Picture Expert Group, also named as JPEG, has taken an initiative to compress multimedia application contents. In particular, their objective is to seek efficient compression solution for light field imaging. And in order to streamline research and development process, JPEG Plano also introduced some common test conditions, which makes the compression method comparable with each other. In particular, these common test conditions specify light field images which are selected from different data sets, bit rates in order to test different bandwidth scenarios. It also specifies the reference compression method with whom one can compare his method. In JPEG Plano, the light field is converted into set of the two-dimensional set of views are converted into single pseudo video sequence and compressed using video coding scheme. And also it explains the quality assessment methods. So in my research work, I have mainly followed JPEG-Plano common test condition to pursue and to compare my results. The overall aim of my work is based on the fact that significant coding gains are achieved in video compression with an effort of over 2 decades, and how that information can be used to facilitate live field image compression, and then later on to look into new novel tools that are developed for live field imaging and how these tools can be used to improve the coding efficiency for live field contents. This overall aim is further divided into 2 purposes, where each purpose resulted into a compression solution, and I will cover each solution in coming slides. To pursue the first purpose of my research work, initially the light field representation were investigated in the context of video compression, and then the video compression scheme is further improved to increase the coding gain for light field content. With the joint effort of ITUT and ISO, two coding standardization bodies, in 2003 8.264 was released. Its scalable and multi-view extension were released in 2007 and 11, which enable layer coding. Then with on average coding gain of 50%, a new coding standard was released in 2012 with the name 8.265, and its multi-view, scalable and 3D extensions were presented in 2016. And recently in late 2020, a new video codec with the name Versatile Video Coding 8.266 is released. In this slide, the basic processes that are involved in video compression are explained. The video is given as frame by frame to the video coding scheme, which process each frame block by block. Initially, a predictive coding scheme is used to form a prediction signal, and then the difference between original block and the predicted block is transformed, quantized and entropy coded. In predictive coding, we use 2 tools, intra-prediction and interprediction. In interpredition, each block is allowed to seek prediction from its neighboring pixel. So in this case, the prediction remains within an image. In interpredition, each block is allowed to seek prediction from already encoded frames by utilizing motion estimation and compensation tools. So it depends on previous frames as well. In my research work, I started by focusing on planooptic image compression. On the left side, a sub portion of a planooptic image is shown, which shows microlens images as well. The planooptic image can be converted into multiple perspective images, also referred as subaperture images, by sampling a specific pixel from each microlens. Subaperture images are generated. Each subaperture image represents the scene from a specific perspective, and this representation of planooptic camera is also comparable with light field capture using multi-camera system. And both of these representation can be very well represented using 2-plane parametrization, where UV coordinates indexes the camera plane and ST coordinates indexes the pixel of image. In my proposed work, I interpreted this 2-dimensional set of views from planooptic camera and multi-camera system as multiple pseudo video sequences, and I applied a multi-view coding approach. In particular, I used multi-view extension of high efficiency video coding, which was the state of the art tool at that time. The multi-view extension of high efficiency video coding is introduced for multiple video camera system. Here an example of 2 video camera streams with 2 frames is shown, and basic working of multi-view HEVC is explained. Initially, the first frame of first video is encoded using intra-coding scheme. At the same time instant, The first frame of second video stream is encoded by seeking interview correlation from already encoded frame in the neighboring video stream. The second frame of first video stream is coded by seeking temporal prediction from already encoded frame in the same video stream. And finally, the last frame is encoded by seeking temporal and interview prediction. So this multi-view HEVC framework enables each frame to seek two-dimensional prediction from its already encoded neighboring frames. Initially, an experimentation was performed on sub-aperture images of balloon optic camera, and comparison is made with JPEG plano anchor scheme, which shows significant coding gains, and which motivated to further investigate multi-view HEVC and to develop a light field compression solution on that. In proposed compression scheme, the frames of multiple pseudo video sequence are organized in hierarchical level in such a way that frames placed in higher hierarchical level are assigned with better quality compared to the frames that are placed in subsequent level. Here an example of single row of light field is shown with 5 views. The prediction structure utilizes this information, and it uses high quality reference picture for prediction of remaining frames in order to improve the coding efficiency. The hierarchical coding in proposed scheme is achieved by specifying a specific quantization parameter to each view. Here an example of 5 by 5 views is shown. The quantization parameter regulates the trade-off between bits and quality. The higher the quantization parameter is, the worse will be the quality and less will be the bits. The central frame, also referred here as a base frame, is assigned with the initial quantization parameter value. This frame is encoded first in my proposed scheme, and it is assigned with best available quality. And for rest of the frames, a quantization offset is estimated and added with this initial quantization parameter to get their quantization parameter. The quantization offset is estimated by considering the distance between current frame and the base frame, which means that it is giving high importance to the central frame. And secondly, it is also considering the encoding order of current frame relative to the first frame, center frame. So the frames which will be encoded first, they will be given high importance since they will be used in prediction process. And using these two aspects, a quantization offset is estimated. To quantify the benefits of having hierarchical coding in proposed compression scheme, a comparison is made with uniform coding scheme, in which fixed quantization parameter is used for all the views. And it is demonstrated that around 0.5 dB improvement in PSNR is achieved by using hierarchical coding scheme. The variance in PSNR at each bit rate is also shown, which reflects that the proposed scheme incurs twice variance compared to uniform coding scheme, and the influence of this variance is high at high bit rate. Secondly, the motion estimation process in proposed compression scheme is investigated. In motion estimation, a search is performed on reference picture in order to find the best matching block for current block by using sum of absolute difference criteria. For rectified light field, it is proposed to reduce the two-dimensional search space into a single dimension. For example, if the current block and the reference picture lies in the same row, so only horizontal direction search should be performed, otherwise search should be performed in vertical direction. Secondly, since light field captures the same scene from different perspectives, so high correlation exists in the contents and also in the encoding decisions. In my proposed work, the central column of light field is encoded first, So, the maximum motion vector information found in the central column is used to set the motion search range for rest of the views, and in experimentation it turns out that it remains consistent. Using these two optimization in motion estimation process for light field compression, around 80% reduction in SAT computation are reported in motion estimation process with a negligible loss in coding efficiency. Finally, the multi-view HEVC based proposed light field image compression method is demonstrated on subaperture images of balloon-optic camera and views of multi-camera system. The rate distortion comparison is made with JPEG plano anchor scheme and also with state-of-the-art scheme in case of subaperture images, which shows that the proposed scheme performs better compared to the anchor schemes. However, proposed scheme also has few limitations. At extremely low bit rate, the quality of proposed scheme and also the anchor schemes are limited. And due to the nature of the hierarchical coding scheme, which assigned a variable QP to each frame, it is also difficult to achieve a target bit rate. In a very recent study, a comparison is made among state-of-the-art light field image compression methods, in which each method is compared with JPEG plano anchor scheme and saving in bits is reported. The result shows that the proposed scheme on average perform better compared to state-of-the-art schemes. Now, I will come to the second purpose of my research work. In order to pursue the second purpose, a view synthesis scheme is investigated in the context of light field image compression. In view synthesis, the scheme aims to produce new perspective of the scene by using limited amount of data. It may be use a sparse set of views or some geometric information from the scene to produce the new virtual views. View synthesis can be realized in light field image compression. For example, from the original input views, one can select a sparse views and compress them, and then utilize view synthesis scheme to reproduce the decimated views. The Shearlet transform based view interpolation scheme has shown state-of-the-art performance compared to the other schemes, and it only requires disparity range information in order to interpolate the missing views. Here a basic working of Shearlet transform based view interpolation is explained. Figure A shows the views captured using an array of camera, and views are placed according to the disparity range information. Horizontal slicing the V T axis give rise to epipolar plane images as shown in figure B. In epipolar plane imaging, the scene contents objects are represented as lines, where the slope of these lines reflects the depth of the objects. So, having decimated views in between will give EPI image with missing regions, and it becomes a in painting problem in EPI domain. Shearlet transform filters as shown in figure C are applied on EPI image in iterative manner in frequency domain in order to reconstruct the missing region of EPI image, which in turn solve the problem of view interpolation. In this slide, a single iteration of Shearlet transform based view interpolation is explained. The input EPI, which has missing regions, is multiplied with Shearlet analysis filter in frequency domain. Then a hard thresholding is performed to select the coefficients with highest energy. and then again these coefficients are multiplied with Shearlet synthesis filters in frequency domain, and EPI image is reconstructed for single iteration, and this procedure is used for in iterative manner until the convergence criteria is met. Again, an initial experiment is performed to see the benefits of using Shearlet transform based compression scheme. Figure A shows that a sparse set of views are selected from input light field and remaining views are discarded, and they are compressed using video coding scheme. So, a significant amount of data is already discarded, which reduces the bit rate. And on the decoder side, Shearlet transform based view interpolation is applied to reconstruct the discarded views. The result shows that the proposed Shearlet-based compression scheme performs significantly better in low bit rate compared to video coding scheme, which perform better in high bit rate. And the crossover of these curves is on fairly high quality. At extremely low bit rate, it can be seen that proposed scheme retains most of the information compared to the video coding based scheme, which shows blurriness in the contents. This motivated to further develop Shearlet based compression scheme for light field images. Here, the reconstruction error of Shearlet transform is discussed. A 17 by 17 views are shown, where 5 by 5 views highlighted with red borders are selected, compressed and given as input to Shearlet, and Shearlet reconstructed the intermediate views, and the PSNR information is also mentioned. The central row of this grid is plotted in figure B, which shows that when 5 key views were given as input to Shearlet on around 48 dB quality, Shearlet reconstruct the intermediate views on around 41 dB quality. And this reconstruction error is a consequence of two facts. First, the quality of key views, which is given as input to Shearlet, and secondly, Shearlet limitation to reconstruct intermediate view by only using the sparse set of views. So, its reconstruction quality is also limited. In order to improve the coding efficiency of Shearlet transform based compression scheme, the residual error, the reconstruction error of Shearlet transform is also investigated and included in the compression chain. The input light field is divided into two sets, key views and decimated views. The key views are coded using multi-view HEVC based scheme, and at the encoder side, Shearlet based view interpolation is used to interpolate the decimated views. The original decimated views and interpolated decimated views are used to calculate the reconstruction error, which is compressed using intra-coding scheme. On the decoder side, the key views and reconstruction error is used to reconstruct the input light field. In developing the proposed compression scheme, the coding of reconstruction error was also investigated. Here again, as explained, from input light field, a sparse set of views are selected, and these views are compressed on different bit rate. Here, for example, from R1 to R4, where R1 shows the highest bit rate and R4 the lowest one, and then Shearlet transform is applied to reconstruct the intermediate views. The mean PSNR of these reconstructed views is plotted in figure C on bit rates R1 to R4, and it can be seen that the reconstruction quality of Shearlet is not coping up with the quality of input key views. Two bit rates are selected, R1 and R3, and reconstruction errors is calculated and coded using intra-coding scheme and intercoding scheme. and compensated on these 2 bit rates. This rate distortion analysis reflects that both intra and intercoding scheme has same amount of coding efficiency. So, in my proposed research work, I selected intra-coding since it is computationally efficient and it does not require reference pictures. Secondly, on these 4 different bit rates, error is compensated on all 4 bit rates by compressing the error on different bit rate. And it reflects that allocating more bits to key views so that they can be encoded in high quality and given as input to Shearlet, it is more beneficial to allocate those resources of bits into reconstruction error coding, which significantly improves the coding efficiency. Finally, Shearlet transform based light field image compression scheme is demonstrated on different light field images captured using different multi-camera based systems, and results were compared with state of the art light field image compression method, which was multi-view HEVC as I proposed earlier, and also with JPEG plano anchor scheme. The result shows that the proposed scheme performs better in low bit rate, and HEVC multi-view HEVC based scheme perform better in high bit rate. And it can also be seen that by incorporating the reconstruction error of Shearlet, the coding efficiency improves. However, the proposed scheme also has few limitations. It is computationally expensive it is making the requirement of computations at decoder side higher, since it is invoking Shearlet transform based view interpolation over there. And also its implementation in the encoding loop of video encoder is a challenging task as well. Finally, I will conclude my talk and will explain some possible future directions that can be take from this work. The representation of planoptic image also influences the choice of compression method that will be used. Initially, researchers look into lenslet image representation of planoptic images, and they modified image coding scheme to improve the coding gain for planoptic images. Later on, subaperture image representation of planoptic image is explored, and this representation enable video coding tools to exploit the coding efficiency for light field content, and also it gives an opportunity to develop a generalized compression solution for planoptic camera and multi-camera system. However, converting the 2-dimensional set of views into a single pseudo video sequence restricts the interview correlation into a single dimension. And secondly, it also conflicts with some advanced tools that are implemented in video coding scheme, such as motion vector scaling, which assumes that the frames are captured on a specific time, and it uses that information to scale the motion vector and improve the coding efficiency. The interpretation of 2-dimensional set of views as multiple pseudo video sequence enable each frame to seek 2-dimensional interview correlation that is available in the captured light field data. Secondly, the concept of dividing the light field into 2 sets using video coding scheme on one set and then using a novel tool to reconstruct the second set can be seen in recent state of the past art works. Researchers are using new novel methods in similar strategy, where one set is compressed using video compression method and the second set is interpolated or synthesized using graph based methods, deep learning based method. So, it is becoming a common trend in this field. However, these methods also make a trade off between complexity of encoder and decoder side, since they rely on sparse views. So, complexity is at the encoder side reduces, and they invoke the method of like weave synthesis method on decoder side, which increases the complexity over there. Now coming towards the future directions that can be derived from this work, my work was mainly focused on objective quality assessment of light field images, which has its own benefits as well. It's make the method comparable, less expensive, easy to perform. However, since light field can be presented to in multimedia applications made for human vision system, so assessing the quality using subjective quality assessment methods can give more insight about the coding scheme. And it will be very interesting to look into comparison between Shearlet-based light field image compression and multi-view HEVC-based light field image compression. Secondly, deep learning is finding its way in many applications, and one can also look into footprints of deep learning in compression as well. Since light field data capture the same scene from different perspectives, so high correlation also exists in encoding decisions, and video encoder takes complex decisions to achieve the coding efficiency. So one can use machine learning method to speed up the encoding time for light field content. In recently, various researchers have started looking into different requirements of compression, like random access, scalability, region of interest for light field contents, and these aspects can be investigated in the proposed scheme as well. And also, to achieve a target bitrate, one can look into the rate control mechanism of multi-view HEVC and how that can be optimized for light field contents. I would like to thank you for listening to my talk and to looking into my research work that I have done in past 4 years. Thank you so much.
Thank you very much, Waqas, for this interesting presentation of your work. It is a summary of 4 years of work, so it is not easy to squeeze everything into these few minutes that you have. Now we will take a few minutes of break in order to reorganize here. So this is the time when you can stretch your legs and breathe a little bit. We'll take 5 minutes, and then the dissertation will continue with the discussion between the opponent and the respondent. So 5 minutes break now.